All right, now let's talk about local models of cost functions. As we discussed, many optimization algorithms rely on constructing a sequence of quadratic models of the cost function and then using minimization of those to generate the next iterate, right? So many sort of optimization algorithms sort of rely on sort of local quadratic models of the cost function to generate iterates. Okay, and of course, as you might expect, it's like what you do is that you take that local quadratic model, you look at the critical point, and that becomes your next iterate, or it's related in some way to that. Okay, so we'll review sort of the construction of such models. In Rn, in general vector spaces, and then generalize it to Riemannian manifolds. Okay, all right. So let's look at the case for Rn. So okay, so let me state a proposition. Okay, so let f be a smooth real valued function. On Rn. Okay, and you have a point x which is in Rn. Okay, and U is some sort of bounded neighborhood of X. Okay, and H is any symmetric matrix. Okay, then the following is true. There exists some constant greater than 0 such that for all points x plus h, right, in this neighborhood U, okay, if you look at the difference between f evaluated at the point x plus h and sort of this quadratic model of it, right, which is, if you will, looks something like a Taylor expansion, right? So f of x plus the derivative of f times h, right, plus some sort of quadratic term, 1/2 h transpose h, right? Then, okay, you know that basically, if this h isn't the Hessian, right, then in general this is only going to be a good linear model, and then the error, right, in that case is going to be bounded by some constant h, some constant times h squared, right, where, of course, the f of x is these sort of vector of first partials, right, d1 fx, right, dn right? So it's like the gradient, basically, right? Okay, so if, moreover, right, hij, right, is equal to this mixed partial, right, then again there exists some constant c greater than 0, such that, again, for all x plus h in this bounded neighborhood of u, about x, I'm sorry, then this function, right, is well approximated by this quadratic model, right? The error scales like ch cubed, then, right? Okay, I'm sorry. Well, h is a vector here, so it really is the norm of h here. I'm sorry. This is the norm of h as well, h cubed. Okay, all right. So this is really just sort of Taylor expansion, right? But in the multivariate setting. Okay, so that's not too surprising. So let's then ask, well, what happens in general vector spaces? And then once we have general vector spaces, the case of general vector spaces, then we can talk about the case of a Riemannian manifold. And essentially what's going to happen is that on the Riemannian manifold, right, we're going to take advantage of the choice of a retraction, right? And then the retraction allows you to take a cost function, a smooth cost function on the Riemannian manifold, and then think of it as a smooth cost function on a tangent space, which is one of these sort of general vector spaces, and then apply the results, which we're going to talk about, for general vector spaces to that case. Okay, so that's really sort of the strategy we have in mind. Okay, so all right, so anyway, this is sort of fairly standard stuff. Let's see what happens on general vector spaces and then eventually Riemannian manifolds. Okay. Okay, so these are models in general sort of Euclidean spaces. So what I'm going to think of is that it's a sort of a, so we want this on abstract Euclidean spaces. So this is some finite dimensional, oops, so finite dimensional vector space with an inner product. Which we denote by this sort of angle brackets. And then, and the inner product obviously induces a norm. All right, so with that, we're now ready to state the analog of this proposition. Okay, so the main distinction, of course, is that now you have a inner product, right, as opposed to sort of the usual dot product, right, in Rn. And then the induced norm is obviously induced by this choice of inner product. Okay, so what you get is the following. So again, it's like let f be a smooth real-valued function. Euclidean space. Let's call it E, right? And then we have some point x, which is in E, and a bounded neighborhood of x, U, right? And then now, again, you have a sort of, instead of thinking of a matrix, we have a linear operator, right? H, which is mapped from E to E, right? And it's symmetric, right? So that's the analog of a symmetric matrix, right? It's a symmetric linear operator, right? Well, I should say symmetric linear operator. Okay, then there exists, again, a constant greater than 0, such that for all x plus h, which is in U, as before, right, the difference between f at x plus h and some sort of model of it, f of x plus, okay, now we're going to have the gradient of f here, okay, at point x paired, and then you take the inner product between that and second h, right, okay, plus 1/2 h applied to this vector h, right? So this gives me another element of the Euclidean space, and I can pair that with h, all right? And then the error is, again, bounded from above by some constant c times the norm of h squared. All right, and then if, moreover, h is the Hessian, f of x, right, which is a map from h to d of the gradient of f of x and h. Again, you want to think of this as a linear map from h to this object, right? Then, again, there exists some constant greater than 0 such that for all x plus h in this bounded neighborhood U, right, which contains x, right, then you have that f of x plus h is approximated by this quadratic model. And the error you introduce by doing this is bounded from by some constant times the norm of h cubed, right? So, all right. So in particular, obviously, if h is just the trivial operator which maps everything to 0, right, then you're just left with this sort of first order Taylor approximation, if you will, of the function f, and then you know from the Taylor remainder term error theorem that the error is big O of h squared, right? And then if you have that this is actually the Hessian operator, right, you get something which is big O of h cubed. And again, the main difference between this and the previous result we had in Rn is that in Rn we had assumed that the inner product was just the usual dot product, right? So you have some simplification of these expressions here. But then more generally speaking, we want to set it up in this language, right, which then will naturally lead to what happens when you have a Euclidean, when you have a Riemannian manifold, which has obviously an inner product at each point in the tangent space, in the tangent bundle, and you know, you have you want to think of the Hessian operators, it's like in the gradients here. Okay, anyhow, so that's sort of the setting which we have. I'm just going to write this model here as mx. If you will, at the point y, right, as being equal to, well, I'll just leave it here. It's all right. Okay, so anyway, so let me just, well, maybe just write this down, right? So this is f of x plus the gradient of f at x paired with h, right, plus 1/2 h acting on h paired with h, right? So that's sort of, you know, the analog, if you will, it's like of the Taylor expansion. Okay. So let's now try to do this. It's like on a Riemannian manifold. Okay. Okay, so we're now looking at models on Riemannian manifolds. Okay, so now, as before, we let f be a real valued function. On a Riemannian manifold M. Then we have x be a point on M, then a model, so a model, let's call it mx, m sub x of f, right, as a real valued function. Defined on the neighborhood, it's like of x, right? Okay, such that, okay, two things happen. The first one is that one, mx is a sufficiently good approximation of f, right? Maybe in this kind of sense. Okay, and then the other thing, obviously, is that it is easy to compute, or easy to write down, if you will, right? So mx has a simple form. That is easy to address. It's like in the optimization algorithm. Easy to use in an optimization algorithm. Okay. All right. So so let's try to address the first property, which is the question of sufficiently good. All right. So what do you really mean by this? Okay. So we can sort of quantify the quality, if you will, of the approximation. Okay. By sort of, I mean, it's like in, this is what you see, it's like in all these previous propositions, right? You're comparing the actual cost function with this with the model, right? And you want to, it's like quantify the error it's like which is being made, right, in terms of essentially the distance between the 2 points, right? Sort of comparing. Okay, so what I'm doing is I'm going to quantify the quality of the model by comparing m sub x evaluated at y, right, with f evaluated at y, and expressing this in terms of, well, actually maybe bounding this, if we will. Maybe it's a better way of thinking of it. Of the Riemannian distance, if you will, between x and y. Okay, so that's basically analogous to this, right? This is essentially f at the point y, and then this is, okay, maybe I should write it this way, right? This is what? This is f evaluated at x plus h, right? And this is mx at x plus h, right? X plus h is y, right? And then this is some constant times the distance between x and x plus h cubed, right? So that's sort of another way of writing this, right? So that's basically what we're trying to do, right? We're going to compare f at some point y with the model which is constructed at the point x but evaluated at the point y, and we want to look at the error it's like you introduce by replacing f of x with this model and expressing and bounding that error it's like by something which involves the distance between the point x and y. So that's analogous to what we have here. Okay. Okay, so all right, so let's make this more precise, right? The model sub x, right, is an order q model. Q greater than 0 if there exists a neighborhood u of x in M and a constant, again, c greater than 0, such that, right, the difference between f at y and the model which is constructed at the point x but evaluated at y is less than equal to some constant times the distance between x and y to the power q plus 1. And this is true for all y in this neighborhood. Okay, so this is really sort of the natural generalization of what we had before. Okay, so in particular, this is that any Q order model, any order Q model, automatically satisfies the following. So it automatically satisfies the property that f at x, right, is equal to mx at x. Okay. So, all right. And that's because it's like when you put x here, so you have f of x minus mxx is less than or equal to some constant times the distance between x, and that's 0. So when y is equal to x, right, that error you're making is 0, so it has to be that f of x is equal to mxx, right? So that's sort of obvious. Okay, and what's going to happen basically is that we're going to relate this now. Okay, again, the motivation is to do this on a manifold, and so we're going to show that we can study the order it's like of a model by using the retraction. Okay. All right. Okay. Okay, so let f be a real valued function on a Riemannian manifold. Well, and let x be a point on this manifold, right? So a model, let's say mx of f, right, is order q, right? If and only if there exists a neighborhood u of x and a constant c greater than 0 such that, okay, f of x, f of y minus mx of y is less than equal to constant times the norm of the inverse of the retraction. Okay, so I'm replacing the distance, it's like by the distance, it's like which is induced, it's like by this retraction, q plus 1 for all y in u. Okay, and essentially the idea is that, you know, again, it's like this notion of approximation and convergence. It's like oftentimes only really matters when you're really, really close. It's like if to the point. Okay, so you only really have to worry what happens. It's like when y is very close to x in some sense. And then intuitively, it's like the local rigidity property means that, you know, at least locally, this is very close to the distance, right? So that's sort of intuitively why you can study the order, it's like of approximation in terms of this induced distance which comes under retraction. Okay, so anyway, so let me just prove this. Okay, so because of the local rigidity property, right, it follows that you have the following, right, d of the exponential inverse composed with retraction at the point 0x, right, is the identity, sorry, it's the identity map on Txm. Okay, so what that means is that you can say something about the operator norms associated with this. Okay, so this implies that our x inverse applied to y, the induced norm of this, is equal to the induced norm of this object. Right, so all right, so essentially what I'm doing is that I want to compute the induced norm of this operator, right, and then I'm essentially composing it with the exponential and its inverse, right, and then applying sort of this sort of norm inequality. Actually, I'm not doing that yet. Right. This is composed with the exponential, right? Okay, all right. Sorry, I'm actually not doing the induced norm. I'm actually evaluating it's like the norm of this object, right? Okay. Okay, and so this is omega. It's one of these sort of asymptotic notions. Omega of the exponential x of y, right? Because this term here is like the identity, right? Okay, so this is equal to that. And this is omega of the distance, if you will. Okay. All right. So this is one of these asymptotic. It's like notions like big O. Okay. I won't go into the details. So basically, what it means is that there exists a neighborhood U, okay, of X, and constants C1 and C2, such that C1 times the distance between X and Y is less than equal to the norm of this retraction. It's less than equal to C2, distance between X and Y. Okay, so this is like a, this is true for all Y in U. Okay. All right. So in any case, it's like there's essentially an equivalence. It's like between these two norms. It's like which are induced by the distance. It's like in this retraction thing. Okay. And so it's like for the purposes of any kind of notion of order of approximation, it is perfectly reasonable to replace the distance. It's like with this object instead. You know, at the cost of changing the constants, basically. But that's doesn't matter. Okay. All right. So anyway, so this gives you sort of, you know, it's like a nice characterization. And the next thing we're going to do is to talk about how to actually construct these local quadratic models on a Riemannian manifold through the use of the retraction. Okay, so let me just stop here for now.